So, how was the sessions are going? Whether you can understand?
They were good.
Yeah, they're good. Interferometry, how you were feeling? It's good or
Yes, sir.
difficult or easy? Okay. Today let us start doing this mm, ninth assignments. Ninth, not ninth, eighth. Yeah, ninth assignment. So whether you have to do, whether you are familiar with the MATLAB and Python or any other languages.
Yes, sir, Python.
You are familiar with the Python. Okay. I am actually familiar with the MATLAB. So yeah, if something like a computation thing I want to explain, I may be usually using MATLAB. So if you are much familiar with the Python, actually you can actually explain here how you are going to use different variables as well as how the things can be done. Okay. Now can we solve this assignment? Assignment 9. You are hearing now.
Yes.
Oh. Now we see if two coherent beams with irradiance I1 and I2 interfere, what is the maximum irradiance of the resultant beam? So the answer there.
Sir, screen is not
Oh, okay. Sorry,
visible.
sorry, sorry, sorry. I'm going to share this. Now the screen is visible now.
Yes.
Yeah. Our first question is that if two coherent beams with irradiance I1 and I2 interfere, what is the maximum irradiance of the resultant beam? So the question we can explain in this manner. So you have two light sources. One is having a irradiance. Irradiance means nothing but a intensity. So you are having a light source with a intensity I1 and you are having a light source with intensity I2 and it is producing some light and my I2 is also producing some light. And these beams are going to interfere. The question is that one, what will be the maximum irradiance or maximum intensity at this plane? If a source of I1 and I2 is got interfered, what will be the maximum intensity which you can get at this plane? How you will calculate this one? No, this is actually not a direct question. Not to understand, you have to know how interference is occurring. So what are the things actually going to interfere to whether intensities will interfere or not? That's my question. Whether intensities will interfere or not. You can tell if you have idea about this intensities can interfere or not. You're hearing that?
Yes, sir.
Yeah. Whether intensities can interfere? What do you think?
Sir, they can interfere.
Actually, intensities cannot interfere. What is the
Where?
thing which is interfering? Actually, the interfering things are electric fields. Okay, electric fields can interfere, and
Okay.
intensities will come as the
Outcome.
or the outcome of the interference. Normal electric field can also give an intensity outcome, and if one light source is there, actually it is producing a electric field, and it is producing a corresponding intensity. And whatever we are seeing like that way, seeing some portion like okay, light is coming from the what you are seeing, we are detecting our intensity. And if some photo detector is detecting some light, what we are detecting, that is actually intensity. But electric field we cannot detect or see. Why we cannot see electric field as electric field? Some idea? What is the thing which we cannot detect?
We can only have potential difference.
Yeah, potential. Actually, you can see the potential difference we can detect,
Yes.
but electric field as a whole we cannot detect. Why?
Yes.
We cannot detect it because original electric fields are complex in nature. Okay, we cannot detect a complex quantity. We can detect only its we can say the complex amplitude product. That's like intensity. So it is like a product of complex and it's a conjugate. So what it will give? It will give the magnitude of that complex number. Okay. Similar way, we are detecting a light as intensity because it is coming as a complex electric field. Okay. So we have to understand how these fields are getting interfered. Now I said that okay, some light, actually from a light source we can see intensity, but the light source is producing a complex amplitude. Okay, but we are seeing only the
Yes.
intensity part. So it will have a complex amplitude E or E1. So it will have a complex amplitude part E2. It's a vector quantity. Okay, now we can see that how we can define. So in the terms of a complex thing, we can write E1 as a E1 naught. It is a amplitude part, and we can put a phase part exponential I some kz minus omega t plus some particular phase factor epsilon 1. Okay, E2 also we can write some E20 exponential I into kz minus omega t plus E2. Now we are thinking that the both source have almost the same amplitude. That's why this kz minus omega t we are taking it as a kz minus omega t only. If they have different amplitude, different frequency or wavelength, we have to take a k1z minus omega 1t, like that we have to take. But here actually we are saying that two wavelength or two sources having a same frequency with some phase difference, that phase factor is given by epsilon 1 and epsilon 2, is going to interfere. This is the original thing. It is producing some I1 and E2 is just producing some I2 intensity. So how it will be related? You know how to take a magnitude of a complex number? If Z is a complex number, what is the modulus of the complex number? Mod Z will be square root of Z into Z bar. You know, is the product of a complex conjugate. Complex number and its conjugate product will give a square of the modulus value. Okay. So from these two values, actually I can write as I1 will be equal to modulus of E1 square. Okay. And modulus of E1 square will be like a modulus E1 into E1 dagger. One dagger will be, it's like I am saying that's a conjugate of that one. So what will be the conjugate? So it's like a E10 into exponential I into kz minus omega t plus epsilon 1 into E10 into exponential minus I into kz minus omega t plus epsilon 1. Okay. Got it? What will be the product? This is exponential I into kz minus omega t plus epsilon naught. This is exponential into minus I into kz minus omega t into epsilon naught. So these two terms will cancel and you will get E10 square. So intensity will be equal to E10 square. Got it? I1 will be equal to E1 square and that will be equal to E10 square. Okay. Okay. You're hearing now?
Yes, sir.
Okay. Any doubt in that one?
No, sir.
So I1 is equal to E10 square. You got it? This look like a little bit complicated, but no need to worry. So in that case, what will be I2? I2 will be E2 modulus square, and that will be equal to, it will come like a E20 square. Okay. I1 will be equal to E1 square is equal to E10 square. Okay. This is clear now? This part is clear.
Yes, sir.
Okay. Now I am going to say that I have two amplitudes, or not amplitude, I have two electric field, E1 and E2. Now I am going to interfere. Interfere means what will happen? This net E will be equal to E1 plus E2. Okay. And what is E1? E1 is equal to E10 exponential I into kz minus omega t plus epsilon 1. So you can say that E10 exponential I into kz minus omega t plus epsilon 1 plus what is e2? It will be e20 exponential I into kz minus omega t plus epsilon 1. Okay, if you added two waves, it will be like it's a complex addition of these two things. Correct? Now you can see you want to get a what is the amplitude or the intensity which is coming from this one, this combination. So what I want the net amplitude or net intensity. Net intensity will come as the modulus product of the both amplitude E1 plus E2 square. So what will be the E1 plus E2 square? This will be like E1 plus E2 into E1 plus E2 star. The star is actually complex conjugate of E1 plus E2. Okay. Now you can see what is E1. E1 is like E10 exponential I into kz minus omega t plus E2 plus E20 exponential I into plus epsilon 1 I into kz minus omega t plus epsilon naught 2 into E1 plus E2 star. So it is like a into conjugate of this one. What will be the conjugate of that one? E10 exponential, you can say there will be a minus I into kz minus omega t plus epsilon 1 plus E20 exponential minus I into kz minus omega t plus epsilon 2. Okay. Now how many terms are there? So one term, second term, third term, fourth term. Now you are going to multiply all the combination. This one will multiply 1, 3, 3 and 4. So 1 into 3 plus 1 into 4 will be there. Then 2 into 3 plus 2 into 4 will be there. Total 4 terms will be there. Okay. Now you see that what will be the product if you multiply this one? E10 into 1 into 3. E10 into E10. E10 square. Exponential I into kz minus omega t plus E1. Here epsilon naught into minus I into kz minus omega t plus E1. So this term will get cancelled. Only E10 plus into E10 will exist. So your first term will be E10 into E10 plus what is the second term? 1 into 4. So E10 exponential I into kz minus omega t into E20 exponential omega epsilon 1 exponential minus I into kz minus omega t plus epsilon 2. This will be the second term plus third term 2 into 3 E20 into E10 here exponential I into kz minus omega t plus epsilon 2 here conjugate of first term. So what you will get E10 exponential minus I into kz minus omega t plus epsilon 1 into e to 0 exponential I into kz minus omega t plus epsilon 2. Okay, now this is the first term, this is the second term, this is the third term. Now one more term will be there. See what is the third term? 2 into 4. e20 into e20, e20 square, exponential I into kz minus omega t plus epsilon 2, and the exponential minus I into kz minus omega t plus epsilon 2. This exponential term will vanish and only e20 plus e20 will be there. So plus some e20 into e20 term will be there. Now you can see that what are the things exist here? e10 into e10. So the term will be e10 square. What is actually e10 square? That you already know. e10 square is I1. So you will have e10 square plus here one e20 square is there. So put it there, e20 square plus, then what are the two terms there? You can see that here also this exponential term is like the product of exponential I into kz minus omega t and exponential minus I into kz minus omega t. Here also you can see that exponential I into kz minus omega t plus epsilon naught into I into kz minus omega t plus epsilon. Okay, so here e10 e20 is common, e10 e20 is common. So take that common term e10 e20. Then what are the things? The exponential I into kz minus omega t into exponential minus I into kz minus omega t plus epsilon naught. So what will happen if these two things are get multiplied? I into kz minus omega t. Here minus I into kz minus omega t. This term will get cancelled. Only the two terms will exist like a I into epsilon 1, and here minus I into epsilon 2 will be there. So exponential I into epsilon 1 minus epsilon 2 will be there. And one more term will be there. What is that one? e10 epsilon naught 20 exponential minus I into epsilon minus epsilon 2. Got it? Any doubt in this regarding? This maths looking like a complicated thing, but it's like a straightforward mathematics. Okay?
Yes, sir.
Yeah. Now here also e10, e20 is common. So we can put it like e10 square, I can put like a I1. e20 square, I can put it like a I2. Now e10 e20 e10 e20 plus I can write e10 e20 is I put it as common. Then what is the value here? Exponential I into epsilon minus epsilon 2 plus exponential minus I into epsilon 1 minus epsilon 2. Correct? Now I have one question. You can say that what will be the value of exponential I theta plus exponential minus I theta? What is the value of this equation? Or you can write like right now exponential means e raised to I theta plus e raised to minus I theta. What is the value? Can you guess something? Any idea? E raised to I theta, you can write it in terms of
1.
e raised to I theta plus e raised to minus I theta. That's e raised to I theta into e raised to minus I theta will be 1. What will be the sum? You can write a complex term in terms of like this exponential form. Na? Similar way, e raised to I theta, you can write it as e raised to I theta is a cos theta plus I sin theta. Correct? This one. Okay. So e raised to minus I theta will be cos theta minus I sin theta. So what happens if you added both together, e raised to I theta plus e raised to minus I theta? What you will get? This is a plus I sin theta. This is minus I sin theta. This will get cancelled. What will not cancel? Only the term which does not cancel will be your cos theta term. So you will get a 2 cos theta. So e raised to I theta plus e raised to minus I theta will be 2 cos theta. So now you look at your expression. Here exponential I into epsilon 1 minus epsilon 2 plus exponential minus I into epsilon 1 minus epsilon 2. So what you will get? So your total intensity you can write it as I1 plus I2 plus epsilon 1 epsilon 2 into 2 cos, this is E1, yeah, sorry, E1 E2 into 2 cos epsilon 1 minus epsilon 2. This epsilon 1 minus epsilon 2 is actually the phase difference. You can write it as like a delta. E1 E2, E1 E2 I can write it as square root of I1 into square root of I2. So it will come like a I1 plus I2 plus square root of I1 I2 into 2 cos delta. The delta is a phase difference. So the total irradiance will be I1 plus I2 plus 2 square root of I1 I2 into cos delta. Got it? Now the question is that what is the maximum value of this one? What will be the maximum value of this one? If you are using a particular light source, I1 will be constant, I2 will be constant. So 2 into square root of I1 and I2 will be constant. What is only the variable here? Your phase difference delta. Okay. And if you want a maximum value, what is the maximum value of cos theta? What is the maximum value of cos theta? You are hearing now. What is the maximum value of cos theta? Anybody can tell? What is the maximum value of cos theta?
1.
Yeah. At what point? At the theta is equal to?
0.
Yes. The maximum value of cos theta is 1 at the theta equal to 0. So if you want to get a maximum value of intensity, you can put the cos theta as 1. So you will get your I is equal to I1 plus I2 plus 2 root I1 I2. Now I'll ask the question, what will be the minimum value of this irradiance? What will be the minimum value of irradiance? Then the assignment question, the question is like what is the maximum value of the irradiance? So what will be the minimum value of the irradiance? What will be the minimum value? What is the minimum value of cos theta? Here you use the cos theta
minus
as
1.
1. Yeah, what is the minimum value of cos theta? That will be
Minus 1.
minus 1. So if you put minus 1 here, what will be the intensity? It will be I1 plus I2 minus 2 root I1 I2. Okay. So if you want to calculate the minimum value of irradiance, it will be like I1 plus I2 minus 2 root I1 I2. Okay. This is the first question. So yeah, I wanted to explain this one because yeah, in the slides itself I see that actually yeah, in the slide it was showing like I1 is equal to E naught cos kz minus omega t something, and I2 will be like E2 naught cos kz minus omega t. That is actually only containing the information about the amplitude. So actually you are missing the phase and the complex nature of the wave. That's why you cannot easily come to that original equation like this one. So this equation is actually the one which is important equation. Total irradiance will be equal to I1 plus I2 plus 2 square root of I1 I2 cos 5. You know why this is important? Why this is important? Or why this is a fascinating thing? This equation is actually a very nice thing. What they are saying, so total irradiance or total intensity given by two source will be equal to I1 plus I2 plus 2 into square root of I1 I2 cos delta. So this is what I1 plus I2. I1 plus I2 is the total irradiance if you add the intensities of the two sources separately. So just think that you have a two light sources. You have a light source of 1, and you have another light source, second one. And if you are adding the intensities together, you will get a combined intensities as a I1 plus I2. So this is the thing which is happening normal. Okay, this is the thing which is happening in a normal life. So you can see that if you are adding, like you just light a bulb inside your room, what you will see, your room will be filled with light. So what you will do, you will light one more light. What happens in the room? The total intensity inside the room will be higher compared to your initial thing. So the intensities are getting added, but at a certain condition, this equation suggests that if you are using a phase relationship, yeah, if in your light source the phase relationship can come such a way that if there is a cos term, the phase relationship became -1, the intensities can come like I1 plus I2 minus 2 square root of I1 I2, and this quantity will be bigger than 1 or bigger than 0. So this intensity will be I hashed. This I dash will be always less than I1 plus I2. So it is like if you light, if you switch on two lights in a room, actually the intensities can be lower. It can come out in such a way that, so it's like a light can even produce darkness. or light can produce dimmer light. To light you are adding, instead of getting bright light, you are getting a dimmed light. So that is coming. So it's like a light can produce dark. That's why this equation is somehow important, we can tell. Okay, this too much information is there in that single equation. Now we can check the another question. Now you don't have to worry much. Questions are like it. The fringes of an interference pattern can be thought of as lines connecting points of same. This is like a direct question. It's a direct question. What is the interference pattern is telling? Or interference fringes is actually is a same optical path length area or region. So if you are seeing some interference pattern like on a soap bubble or on a oil spilled in water, if you are seeing some nice interference pattern, if you're seeing some nice interference pattern like this thing, actually the same color or the same fringe is actually corresponding to a particular path length. So each interference fringes is a corresponding to a particular optical path. Okay, each that can be each fringes or that can be each particular color. So the question is that one. The fringes of an interference pattern can be thought as the lines connecting points of the same optical path length. A single frequency laser has a dash coherence than a white light source. The laser has a, what kind of coherence laser has a? It's like a, whether higher temporal coherence, higher spatial coherence, higher spatial and temporal coherence, or none of these. What kind of coherence laser have compared to a white light source? Tell. So I have a white light source and I have a laser source. What is the difference? White light source, laser source. What is the difference between the coherence here? White light source will have a less temporal as well as a less spatial coherence. Temporal coherence means the coherence will die as you are moving along the line or along the time. So if it's a white light source, it will have like a, after some time the phase of that way may be different, or like that way it will go like this way, something like that. But in the case of a laser, we can say that laser can go without much phase change in a very low, very high distance. And what is mean by temporal spatial coherence? Spatial coherence is actually saying how nicely the phases are connected in terms of your particular medium. So in the case of a spatial coherence, you have to see on the surface if they are actually exactly passing similar way, it will have a high spatial coherence. But in the case of laser, all the beams are emitting, and by the stimulated emission of radiation, the laser is emitted and it has a high spatial coherence also. So it's like all waves emitting from one point is exactly looking like same, or it will have a exactly definitive phase relation. Okay. So laser source will have a higher temporal as well as a spatial coherence. Figure 1 shows a part of a Gaussian beam. As it travels along z direction, based on this figure, select the correct option. This is actually the one which is madam give as a practical example. Correct, na? The same as madam given as a practical. Correct? So, what kind of Gaussian beam is this one? What is the coherence information of this Gaussian beam? Can you people tell? What is the coherence information of this particular laser beam? Anybody can tell what is the coherence information of this particular laser beam? You can see all the wavefront along the xy plane, na? This kind of lines, vertical lines. The wavefronts are like exactly following the same path. So you can say this kind of Gaussian beam will have a high spatial coherence, but you can see that here two vertical lines are there. This is actually hindering to give any information about the phase. So there is after some here there is a sudden phase change is happening. So you can say that this thing will have a low temporal coherence. Okay, any doubt? Any doubt?
No, sir.
Now, now we can check the.
No, sir.
You have doubt? Now from here information you can see that this beam has a poor high spatial coherence but a poor temporal coherence. Okay. Now we can check the another question. Which of the following information interference experiment is set up for typically used to test the spatial coherence of a light source? What is actually mean by spatial coherence? It's like the phase relationship between the different points on a particular light source. So you want to measure the coherence parameter of a particular light source at different points of that emitting area. So if it is happening like this way, it's a light source and it will have a different points. Different points and the rays will be emitted from these sources. And if all sources are in like exact phases or there's a definite phase relation, then I will say that my wave will have a good spatial coherence. So it is like this. Now the question is that how we practically measure this one. So in order to measure this spatial coherence, how I can measure? Actually, I want to do some interference experiments with this spatially separated beams. So I have to split these beams and make it to interfere. So what I will do, I have this light source and I will pass this light source through some slit. Then I will have a slit two slits arrangement such that this wave will produce your secondary wavelets, and here also it will produce a secondary wavelets such that this thing will get interfere and it will produce if the light source has a good spatial coherence, and these two interfering beams are actually coming from the same light source, so it will produce a nice interferometric pattern. So it will produce a nice interferometric pattern. So if you are getting this kind of metric pattern, you can say that it has a good spatial coherence. And this arrangement, what is called this arrangement? Which is going to check our spatial coherence. What is this arrangement? Have a two slits arrangement. This is nothing but a Young's double slit experiment. Okay, hopefully it's good. Now the next question. Which of the following interferometer experiment setup is typically used to test the measure the spatial coherence of light source? So the answer is like a Young's double slit experiment. Okay. Now next, a Michelson interferometer with a 50-50 beam splitter. Which of the four? So what we'll do? Which of the following are true about the visibility of the fringe pattern? Okay.
Sir,
Yeah.
sir, I had one doubt about Fresnel and Fraunhofer diffraction. Uh, both of them are the part of double split experiment, or they are something different.
Frontal, how they are saying that it's like a, I didn't go through that portion actually. Yeah. But what they are actually saying, frontal is actually coming when that source distance and source to slit as well as the slit to screen distance is like infinity. That is coming as a Fraunhofer. Na?
Fraunhofer is infinity and Fresnel
Frontal
is
is a finite.
different. So what we have is in Fraunhofer we have defined limits, na, but in Fresnel we cannot. So I wanted to ask that if we are talking about Fraunhofer, was that same as that of double slit experiment, or that was something different?
But this double slit experiment is it's almost like Fraunhofer.
It's almost like Fraunhofer.
Yeah,
Like if we do double slit experiment, we can see it is same as Fraunhofer
yeah. Because whatever you are using the size of your mm,
slits.
slits as well as the wavelength is in such a way that it will produce almost nearly circular fringes, not fringes,
Mm.
circular wavefronts. And
Yeah.
circular wavefronts is like that way we can actually, when the distance is increasing, the circular wavefront can actually we can limit to as a plane waves getting interfere. So if you are using a distance which is like a distance which is much more, and if you can actually compare, it's like a
Mm.
plane waves, actually you can almost consider it as like a Fraunhofer,
Okay.
but the distance should be much higher compared
In
with the that's the width as well as the wavelength of the light which you are using. Then only you can put it like a Fraunhofer diffraction in that case.
so for in experimentation, if we do double slit experiment, so we can say that these are similar to the results of Fraunhofer.
I think if I can actually go through and give some explanation later, but I yeah, but I think it's like similar to Fraunhofer diffraction. I think.
Okay, sir. Thank you, sir.
I'm not sure. I will check and I will clarify it in your uh, our group.
Okay, sir. Thank you, sir.
So the next question is like microsun interferometer with a 50-50 beam splitter. Which of the following statements are true about the visibility of the fringe pattern? So assume that light reflects off a perfect mirror in both arms. So you know how the microsun interferometer is working. Microsun interferometer will have a two arm. So it will have a one source. The light will come and it will have a beam splitting arrangement. So here they told that the beam splitting arrangement is 50-50. So what is meant by 50-50? Half of the beam will go reflected and half of them will go as a transmitted. And at the reflected arm, you will have a perfect mirror. You will have a perfect mirror. What happens after reaching reflected here? This whole light will come back. Here also, the whole light will come back. Then also, what will happen? It will have a, this is like a beam splitter. So some portion will reflect, but we don't care about that portion. So, but we are only interested in the transmitted portion from top. This will come like this way. And some portion will be actually here, it is getting transmitted, but we don't worry about that one. So we are actually interested in the reflected portion of your. So what will happen here? This two portion will get interfered, and you will get a interference pattern here. So how interference? How will be your interference pattern here? How will be your interference pattern here? If your mirrors are actually perfectly aligned, there will not be any interference pattern. You will get a, if that constructive interference is happening, you will get a bright spot. If you are getting a destructive interference, you will get a dark spot. So if you want an interference fringe or something, you have to tilt this mirror slightly in such a way that there will be a interference between two wavefronts like this way happen. And wherever the constructive interference is happening, you will get a bright spot, and destructive interference portion you will get a dark spot. So in this case actually you will get some nice beam pattern.
Sir, sir, can you explain bit again? Like in Michelson interference, we
Yeah,
will have.
you will have a some source.
Yes.
You will have a source that can be a laser source or a monochromatic light source. Okay, so what happens? This will emit a light having a particular intensity, and in that path we will put a, you can say that it's like a semi-transparent glass mirror that we call a beam splitter. So what it will do, we will put a beam splitter at a 45-degree angle. So when this light is hitting here, half of the intensity will reflect at 90 degree.
Sir, beam splitter or polarizers are same or different?
there are different beam splitters are there. Non-polarizing beam splitters are also there. Polarizing beam splitters are also there. Just think that if you put a polarizing beam splitter here, what will happen? What will happen?
It will polarize the things. I'm not sure.
Yeah, in the case of a polarizing beam splitter, okay, I will explain that. Now think that this is not a polarizing beam splitter. So one portion of the light will reflect. Okay, and it will reach at a mirror. Another portion of the light will transmit, and we will keep one mirror at this also. Okay, after reaching here, what will happen? These are mirror na? Mirror will reflect it back, so it will again reach and come to this beam splitter. This will also reflect back, it will come to the beam splitter. What will happen at the beam splitter? It will again go on to split.
Sir,
So
we will send a monochromatic beam of light, na?
yes,
So it will have single wavelength.
yes,
That wavelength will split into two parts
yeah,
at 90-degree.
yes.
So if it's green wavelength, then how it will split? Like
So
I'm
intensity only will be decreased. So you have a high intense beam or in a high intensity spot, you put it in a beam splitter, you can see opposite side some low intensity beam you will see, and this perpendicular side also you will see some low intensity beam.
so it splits that single monochromatic light into lesser amount of intensities.
Yes, actually you can just think that some 100 photons are coming.
Yes.
The beam splitter will allow 50 photons to transmit through that one, and it will allow 50 photons to reflect.
Okay.
So the intensity will be less, and while coming back again that same thing will happen. Out of this 50, so we will think that these mirrors are perfect mirrors. So out of this 50, 25 will reflect this side, and 25 will transmit here. In this case also what happens, out of this 50, 25 will transmit this side, and 25 will come here. But now you see at this position, if you are putting a detector, I am having two beams coming at the same point.
Yes.
I am having some 25 only, here also I am having some 25 only, but I am having two beams coming at that position. And if that beams, how that beams are actually related, you can see that.
There will be interferences or
Yeah,
some
how,
range form.
yeah, how they will interfere. Now I can say that I have a wave.
If they are in the same position, then they
Yeah,
intensity.
now I have a same wave, something like this way.
So we will have intensity and a wavelength graph with to check this one.
We don't want the intensity and wavelength graph now.
Like on one side we will have lambda and another side we will have intensity.
But how you will have a lambda? The lambda will be a constant. Na?
Lambda will be constant. Yes.
Now you see that I am saying that I have a two beams which is having an exact phase.
Yes.
Okay, just think that one portion is actually went to this side and came back through this way, and another is went to this side and came back. And while coming back, if both of them travel the same distance, While coming back also it will be like exactly same.
Yes.
So
It
it will be in phase.
in phase.
So if both are there in phase, you are going to get a high intensity.
Yes.
So the resultant you will get some high intensity if they are interfering in phase. Now just see that this this mirror is a little bit more distance compared with this distance. What will happen? The second beam will come after some time.
Out of here. It
Yeah,
will be destructive interference.
yeah. So you can actually change the path by changing the mirror position. If something like this kind of thing happen, if that
So sir, grating is also same thing, na? While doing grating, we do this thing only, na?
grating, what it will do?
Uh, in grating, what we will do, we just put some specific wavelength of laser light, and we etch on the surface, and then we see that if the fringes are formed or not.
Yeah. Here, here actually, what are the things getting superimposed? You tell.
Crest and crest, rough and rough superimposition.
Yeah. How it is coming? That's the question. This is
How?
this is coming because of one is traveled more and come back, and it is going to sit together.
Yes.
So one is actually traveling more and coming back with respect to another. So it is like a along the path it is moving. Okay.
Yes.
So this is actually called a temporal coherence
Okay.
because one is traveling a little bit more time compared to another.
Another.
So this is actually interference of two beams which is traveled some more extra time or extra distance compared with another. This is actually a temporal coherence.
Yes.
Okay. But in the case of grating, what they are doing, you are going to put a your laser beam. As you told, you put a laser beam and you are going to put a
Uh,
slit. So
yes.
just think that you have only one slit here. So what will happen? This laser beam will come here. It will form, but you may have studied some. There will be some single slit diffraction. So only one diffraction will happen. Okay, this kind of intensity profile you will get. The intensity profile will be like you have a thick intensity this side and you have a some thin thin fringes. You will go like this way. Okay, if you have a two slit, so if you have a two slit, so that is called a two slit diffraction. And if the slit width is like a very small compared to your wavelength of the light, or it's like a point sources, you can consider it as a two slit interference.
Okay.
So in the case of your laser, and you are going to put a two slit, so you will have a combined effect of diffraction and interference. If it's a two slit, what will be the, it's like a two slit interference will produce like a nice interference pattern. Okay, two slit, a single slit diffraction will produce a diffraction pattern.
Okay.
It will be something like, so the combined effect will be something like a, something like this. This is in the case of a two slit. Okay, when you are going to increase the number of slits, and if the wavelength is matching with that one, you are going to get a n slit pattern. You will have a laser and you have a large number of slits, and in that case, what kind of pattern you will get? That is, it will only allow certain order to maximize. You will get something like this, and minimum, and that's the maximum, minimum, maximum, and these are your, this is the,
Interference.
yeah, this is the combined effect of the diffraction and interference of a large number of slits. So, and it will produce, and you can say that this is the first order, this is second order, or you can say that, yeah, it's a zeroth order. Middle portion is like a zeroth order, then it will like a first order, second order. Other side also first order, second order. This is nothing like a, this is actually your,
First order non-linear equations, and then second order. These are the equations of that fringes.
yeah, these are actually, you will get, this is actually nothing. This n slit diffraction means, just n slit means, it is nothing like your diffraction grating. So based on the grating distance as well as the slit width, actually you can get how spatially these fringes are distributed. This is actually a combined effect of your diffraction and interference. But here you see what is actually getting diffracted. The light is coming from the laser beam.
Yes, sir.
So what is getting diffracted? This is, let's consider it as a point source, and it is coming like a circular,
Spherical
yeah, spherical
wave.
wavefront you consider. So actually, what are the things which is passes through? This is passing through from this part of the spherical wave. This is passing through from this part of the spherical wave. This is passing through this part. This is passing through this part. So actually, different position of the same source is actually passing through different points. This is actually coming as a, what kind of coherence? This is not a temporal coherence. This is a spatial coherence.
Spatial coherence.
So in the case of your grating, whatever you are coming and what you are nice pattern you are seeing is actually a effect of spatial coherence. And in the case of a Michelson interferometer, you can actually vary the path length. By changing the path length, actually you will change the amount of light traveled with respect to one arm to the another. So it's like a, one is traveling
Temporal.
more or less, or one is traveling extra time compared to other one. So that actually is called a temporal coherence.
Okay, sir.
Okay.
Thank you, sir.
Okay. So here the question is like that way. And in that case also, you see, actually if two beams is exactly matched together, in the case of a Michelson, you can see what will happen. It will completely, either it can completely coherent. So it will produce an intense spot at that position. If
Yes.
both the light are like exactly out of phase, what you are going to get? You are going to get nothing. On the screen, you will not at all see anything. It will be like dark. So if the light is exactly matching, either you will get a bright or you will get a dark. This is the case in the case of a Michelson interferometer. If the two mirrors are aligned perfect, but you will not get any fringe pattern. But if you want a fringe pattern, what you will do? Now you have a mirror here, you have a mirror here, and you have a beam splitter here. So just think that your waves are coming like a plane, and after this passes through the mirror also, if it is coming like plane, and this is the other waves coming like from this side, and this is also after coming here, it is actually passing one above the other. So if it is exactly matched this one, and if it is exactly in phase, you will get a bright illuminated spot, and if both are like out of phase, you will get a dark spot. You will not get anything in between. In between thing you will get based on your path length. If you are changing the path length, you will get a less intense spot or a more intense spot. Either you can see a bright color or dim color or no color. That's the thing which you are going to get. But you want a nice pattern. What you will do? You will tilt the one of your mirror slightly. One mirror you will tilt slightly such that the light coming will be having some tilt. So it will be something like that. And here actually use the same perpendicular mirror. So light coming will be like a exact parallel. Now you see that this parallel thing and this perpendicular thing is crossed. So when the lights are like a crossing and you are getting a constructive position, and this is also a constructive position, and in between you will have a destructive position. So here you will get a one band, then there is a dark area, then there is a another band you will get. So if you are, that tilt is actually causing to show your fringe nicely. Okay.
Yes, sir.
Okay. So this is actually the basics of your Michelson interferometer. Next, a practical light source whose output beam can be described by electric field E, A exponential j into omega t minus kz, does not have an infinite coherent length because, so so you have a practical light source. What is meant by practical light source? It's a proper normal light source, not an ideal one. And we are just telling the light wave is a, the electric field we can define as a is equal to a exponential I into omega t minus kz. What kind of wave is this one? What kind of wave is this? A exponential I into omega t minus kz. What kind of wave? people are hearing.
Yes, sir.
Yeah. What kind of wave equation is this one? This is a what kind of wave? It's a plane wave or a spherical wave or a Gaussian wave or something. What kind of wave is this? A exponential I into omega t minus ks. This omega t minus ks is only giving the phase relation. All the amplitude portion is exists in A only. So this omega t minus ks is only giving the propagation direction ideas, and the perpendicular plane is a constant. What kind of wave is this one? If your all electric field values are same on a plane which is a perpendicular to the propagation, what kind of wave? This is nothing but a what wave? What kind of wave?
Sinusoidal.
Yeah, sinusoidal is actually the phase changes. This exponential I to omega t minus k set, we can make it as sinusoidal. But how the amplitude varies along this x and y direction, x direction, y direction, z direction. Amplitude is actually constant throughout x and y direction. So it can be represented by a plane which is in x and y direction having infinite dimension. Okay, so this is nothing but a plane wave. This is a plane wave having a particular frequency omega and having a particular wavelength, wave number. What is the wave number? It's 2 pi by lambda. Okay, so this is having a plane wave having a particular omega and a particular wavelength which is passes through along z axis with having extended electric field along x and y direction. So in an ideal case, the frequency is a constant, or if frequency is a constant, the wavelength will also be a constant. So it is actually, if you put a plane wave and you see the phase pattern, you can see the phase will be changing like this man, and it will extend towards infinity. Correct? Omega is a constant, means it is like a infinite extended phase change. Okay, the phase at a different lambda position will be exactly same and it will be extend towards infinity. Okay, this is the case of an ideal plane wave. But why we are not getting a plane wave which is in this kind of ideal in nature? That is actually our question. Why we are not getting an ideal plane wave? That's the question. Why we are not getting a plane wave? Because if you plot the frequency of a plane wave, omega, and if I plot with the frequency of a plane wave along with the frequency, and I plot, I will get a Dirac delta function or like a sharp peak at exactly at one location where our plane wave has a frequency. So this is actually represented by a plane wave which is infinitely extended. Okay, this will go like infinity, and this will also go towards infinity. But in an ideal case only this is happens. But in a real case, what will have? We will have the there will be a finite width of this way. And this finite width is actually implies it is not a single plane wave, but it is a combination of different frequencies. So if you are going to add different frequencies, actually at some position you are going to lose your coherence. If it's a single monochromatic wavelength or frequency, it can extend towards infinity. But if you have a finite width in frequency or in wavelength, you are going to get a addition of a different frequency, and because of the frequencies are adding differently, you are going to lose your phase information after some time. Okay, so just I can say that if you are adding two frequencies, if you are adding exactly two equal frequency, it will get added. But if you add a slight different frequencies, what you are going to get, you are going to get a beat kind of thing. So you will get something like this. So you will have some high amplitude region, low amplitude region, high amplitude region, low amplitude region. So you can say that if you are getting frequencies are getting added by after moving from this high amplitude to low amplitude region, actually here you are getting a very less intensity. So it's like you are losing your the phase is actually changing from in phase to out of phase, such that your net effect of your interference is destructive. So if you are adding different frequencies like this way, you are actually losing the same um, coherence state. So, but yeah, you cannot get an ideal source. All the real source will have a finite width in amplitude in the case of frequency as well as wavelength. So that is actually causing, even though we are saying or representing our light source as a plane wave, we are not getting a infinite coherent light source because the frequency and wavelength component of the source have a finite line width. Okay, so omega has a fine width and k has a fine width, and k width is actually coming from the wavelength. Okay, next, spatial coherence is related to which of the following parameters: size of the source, the spectral width of the source, the power of the source, or the type of optics used in the source. What is the spatial coherence is related to the parameter? So what is actually spatial coherence? The coherence between two points on the same source. So what will happen if your uh, size of the source is much more higher? What is the chance? The coherence can be higher or coherence can be poor. Coherence can be higher or it can be low if the size is high. You're hearing that? The reverse connection. So you know the spatial coherence. So spatial coherence is actually giving the how different points from the source is related in terms of the phase. This is actually given by the spatial coherence. So if the size of my source is less, the chance of spatial coherence is higher. When my size of my source is much more higher, there are more and more emitting points, light emitting points that can give a less coherency. So actually the spatial coherence is actually depends on your size of your light source. Okay. Now a laser has a wavelength of lambda is equal to 614 nanometer. The spectral width is given as delta lambda is 2 into 10 raised to minus 3 nanometer. The laser has a frequency spread approximately how much? Laser has a wavelength of lambda is equal to 614 nanometer. Lambda is equal to 614 nanometer. And the spectral width is delta lambda is equal to 2 into 10 raised to minus 3 nanometer. You want to measure what is the laser has a frequency spread. You want to measure the frequency spread of your laser. So we know that C equal to mu lambda. Mu equal to C by lambda. If you are differentiating this nu with respect to lambda, I will get delta nu can be written as C by lambda square delta lambda. Okay. So you are not taking only the amplitude part, you are not taking the sign. Otherwise, it is minus C by lambda square into delta lambda. But yeah, if you are considering this one, you can get as delta nu equal to C by lambda square delta lambda. Now, okay, what is the value of C? Value of C is 3 into 10 raised to 8 divided by lambda square. What is the lambda square? Lambda is 614 nanometer. 614 into 10 raised to minus 9 square into delta lambda. Delta lambda is equal to 2 into 10 raised to minus 3 nanometer. 2 into 10 raised to minus 3 into 10 raised to minus 9. Okay. Now do the calculation. What you will get? 3 into 2 into 10 raised to 8. 10 raised to 8 minus 10 raised to 3, 10 raised to 5 minus 10 raised to 9, 5 minus 9, 10 raised to minus 4 divided by 614 square into 10 raised to 80. Like 3 into 2 divided by 3 into 2 divided by 614 square into 10 raised to 18 minus 4, 10 raised to 40. Calculate the values. Three into two divided by 6. 4. So it will be like 1.59 into 10 raised to minus 5 into 10 raised to 40. So 1.59 into 10 raised to 9 hertz. So I can check whether your answer is there. So see, it's 1.59 gigahertz. So you'll have the answer. Okay. Any doubt for this one? You have doubt?
No, sir.
Okay, Anirudh is there. Yeah. You understood that question number 7? Because yeah, because when I am teaching, actually I am not at all seeing the screen. So if you put your hand, I will not say. It's better you could have called. You understood the question? Yes or no? Okay, you can type there. I am seeing. In that case, you are saying that polarization will also change. Okay, yeah. In that case, actually, yeah, we didn't told about our hidden job. We didn't told about what will happen in the case of a polarizing thing.
Pardon, sir?
Yeah, we didn't tell about. We only discussed about microsoft interferometer. We will didn't explain what will happen in case of a if that
Sir,
big.
you said you will tell about
Uh,
polarizer later.
yeah. But yeah, now only I got.
Yes.
Now you see that what will happen. What is actually mean by the polarization? What is the
It's like splitting of negative and positive charge, and extra charge will remain at some point.
oh
So it's polar.
yeah. That polarization is actually that also we can say it's as a polarization. But in the case of an electromagnetic wave, the polarization is the direction of your electric field vibration. So I am saying that can you okay, I will draw one thing. Now you just think that why this interference is happening in a crude manner. Why the interference is happening? Just think that you have a wave,
Yes.
okay, and this wave is actually on a, I will say this is on the, this is my z direction, and this is a x direction, this is a y direction. It's x, This is Y and this is Z. Okay, you
Yes.
know vector addition, na?
Yes, sir.
Yeah, vector addition. So just think that you have a plane wave which is having this kind of direction, and the polarization is actually giving you this one. So if you want to happen a full interference, like a constructive as well as destructive, what you want a constructive as well as a destructive interference. So just think that there is an exactly another wave which is actually coming in the same direction. What you will get? This will add up and form a
Higher intensity wave.
higher intensity beam. Okay. Or just think that if the similar size of wave is out of phase, so it is like a out of phase is there, what will happen? It will combine and form nothing. There will not be any intensity here. So if you want to get a maximum intensity or you want to get a minimum intensity, you want the beam should be added exactly in phase or out of phase. Now see what will happen in case of your polarization changes. What will happen if you have a same kind of beam but it is in a polarization, but this waves is actually x-polarized, because actually this wave is actually on the xz plane. Now I am going to add a y polarized beam with the same amplitude, so it will go like this way. Okay,
Okay.
so if you are looking at from this side, you can see that one wave is like this, another wave is like this one.
Yes.
So what will be its combined effect? It will be another wave which is in this direction.
Yes.
There will not be like combining and becoming zero. In order, you can see that yeah, if you have a wave in a particular plane, this is like you are looking from in front of your wave, and you can see that wave is at in this particular direction. In order to make it zero, actually you have to require another wave exactly in the opposite side, then only you can make it as like a zero.
Yes.
But yeah, just think that if you get a wave which is perpendicular, whether you can make it a zero with these two things.
No.
No, it will be like another beam which is actually shifted. It's a combined beam will be having a different plane of vibration.
Yes.
So that you cannot never get a proper destructive or constructive interference if your plane of polarization change. This is like actually yeah, but just think that if you have a one wave here and another wave like this way, so actually you can get a component of this wave on this plane such that it can contribute in some interference. But if exactly if these two beams are 90-degree out of polarized, you cannot use the two beams and get a interference pattern. Okay.
Okay.
Yeah. Now
So
come. Yeah.
that means in case of polarized beam, the intensity will never be zero and it will never have a maximum intensity.
Yes. Yeah, if you are going to use, and if you could exactly put the two polarized beams in like a perpendicular manner, and based on this orientation, like this way, if you oriented this like that way, if you exactly like the same, it can either produce a plane polarized beam at a different polarization, or if it is like a 90-degree out of phase, it can produce a circularly polarized beam, but it cannot make it your first beam to zero or first beam to maximum.
Okay.
So if you use a polarizing beam splitter in microsun interferometer, and just think that it is at the last plane, it is not giving like yeah, 90-degree out of polarization, then if you are getting two orthogonal polarization, then you cannot get a interference pattern.
Okay.
Okay.
So, if we need the maximum intensities or value of intensity, then we have to choose non-polarized beam splitters.
Yeah.
And if we want to decrease the intensity, then we will go for polarized beam splitters.
No, if you want to get a polarizing beam splitter, what will happen? You will not get interference. You will get a
Okay.
combined polarization only. You will not at all get any interference.
Okay.
Yeah. This is actually we will use in terms of some research purposes. Just think
Yes.
that yeah, some optical teaser experiment. You will see that you want to use two laser beams. How the two laser beams will come? One laser beam they will use. They will this laser beam they will split into two using a beam splitter. So one laser beam will come out, one will go here, and after using some mirror, they will, and here will be some beam splitter kind of thing, and they will pass, and these two beams will go side by side. Okay, why these beams are required? Maybe this may be using like some biological samples collection or something in the microscopic level. Actually, what will happen? Two beams will irradiate to your sample. This is your one beam, and there will be another beam. Okay, and you want these two beams to be interact with your point of interest. Okay,
Okay.
now you think that if these two beams are actually in the same polarization, and you see these are actually coming from same source, so there is a chance that these two beams will interference each other, and it will produce some fringe pattern or some combined effect can be produced inside your cell.
Okay.
So in order to avoid the interference effect, what we will use in between, we will use some
Non
yeah, you will use a
non
not non-polarizing. You will use a
polarized one.
polarizing one. So what happens? This will be at a particular orientation, and this will be another particular orientation. Even though they combine together, it is only going to change at the point of combination. It is going to change the polarization of your light only. It cannot give some high intensity or low intensity due to interference. Okay?
Okay.
Yeah.
Sir, this is known as what? Like we have taken a beam, we have taken a laser beam, then we have taken a beam splitter.
Mm.
which is polarized in nature,
Mm.
because we don't want intensities to be shown.
Yeah,
Then we have taken 45-degree this splitter, projected onto one mirror,
yeah,
splitting both the lights. Then this mirror is projecting the light at 90-degree.
yeah. If it's a
And
45, it will be
it's a
projecting at 90 degree.
and then this next mirror will be projecting onto,
This will be again a beam splitter.
this is again a beam splitter.
Yeah.
Why are we using second beam splitter, sir?
So I want now. I want two beams together.
Okay.
Here only I have one beam. Now you can see that these are two beams together. One is a X polarized beam, another is a Y polarized beam.
Okay. And sir, sample will be placed when where these both yellow and pink beam will
Yeah.
be coming.
Yes. So this is actually a inference I give. So this is actually like one of my research work. So there will be like a very small microscopic area. There I will have a two beads. You may have heard about the optical tweezer.
Yes, sir.
Yeah. In the optical tweezer, what will happen? There will be two polystyrene beads will be there. This will be like micron sized beams, and two laser beams will be irradiating here. And this beams are actually trapped by these laser beams. So this will be all in my small microscopic dimension. So in between actually my sample will be there. Okay. But just to think that actually this this laser beam will move according to the our requirement. This either this side as well as the other side.
Sir,
But
you are placing spring in between them.
no, this will not be a spring. I am saying that this will be either a DNA coil or a protein molecule or something like that.
Okay. Sample to be tested.
Yes. So based on the force, actually you can change this laser beam's orientation. But the thing you are saying that this will be like everything will be like a small microscopic slide only. So there is a high chance that this laser beam can interact with this laser beam. So in that case, if the laser beams are got interacted, if it is going interference, and if it is something like that, if it is a destructive interference kind of thing, you have a big chance that on the spot of the destructive interference, you will lose all the power of your laser at that point. So you
Yes,
don't
sir.
want that one. So what you will do, you will, so this is like this laser beam is coming here and it is reaching here. One will be here, one will be here. You will make this is X polarized and this is Y polarized in such a way that this will not get interfere.
Interfere in each other.
Yeah. So this is like one application.
Okay, sir.
Yeah. And coming to our Anirudh's question, so this like a, yeah, in the plane wave actually plane actually we will not say any particular polarization. We are thinking that all may have in the same polarization, but this amplitude and what is called wave number have a characteristic width even if your polarization is a constant. But yeah, in the ideal case we don't need to tell about any polarization there, because we cannot say that after passing through a finite distance the polarization will change, because this is like a waves are oscillating in a particular direction. So in the case of a plane wave, there it's like we cannot say that there will we cannot say that there will be a finite change in polarization over time or over distance or something. I think that's why they didn't told like polarization is a constant. Okay. Now the question, 10th question. In the laser described in the problem above, this means that every dash seconds the wavelength shifts to some value within lambda plus delta lambda by 2. What is the value? When there is a, now we given that delta lambda is 2 into 10 raised to minus 3 nanometer. So within that particular time, the wavelength is changing in between lambda plus or minus delta lambda by 2. That time is actually called, it has a particular name. It is called coherence time. How you will get a coherence time? That will be reciprocal of your frequency shift or frequency spread. So what is your frequency spread in the above question? So you can say coherence time Tc, you can write it as 1 by delta nu. You already got delta nu as a 1.59 into 10 raised to 9 hertz. So Tc will be 1 by 1.59 into 10 raised to 9 hertz. That's 1 by 1.59. It will be like a 0.628 into 10 raised to minus 9 second. 10 raised to minus 9 is actually nanosecond. So you can get a 0.628 nanosecond. Okay, this is the answer for that question. Got it? Any doubt regarding any other things? In between, Raju sir was saying about something about the assignment problem 9. Let us just go through assignment 10. What is they are saying? Micro center is one of the like one of these methods. Dark past okay, this interferometer part actually you people are telling. Okay. This actually I think she described in her lecture in a nice manner. By seeing your nature of the lines, actually you can understand that what kind of wave fronts are getting interfered. Anyway, I cannot tell the much more about this assignment since we have assignment submission date is still pending. But yeah, you have any specific doubt regarding this one, you can just put it in your group, or you can, if you can tell, you can tell what kind of, other than this direct assignment question, you can tell what are the problems which you are facing. If it is not given in the lecturer, I can just give, I will go through that one and I can just put it in the assignment. So any more doubts?
No, sir.
Okay, so can we stop? If you people have any doubt, you can just put a comment in that one such that I will go through that one and okay. Thank you.